The kinetic molecular theory is the simplest model for the behavior of gases. And I think it's, actually quite straightforward. The idea here is that a gas is modeled as a collection of particles. Those could be molecules or atoms. Collection of particles that are in constant motion. So here we have this, illustration of a flask here, and we've got these little dots, and they're leaving these little trails behind because that's supposed to indicate motion. And you think of those as just bopping around in this flask. They're going to travel in a straight line until they run into something. They may run into the side of the container, and then they're just going to bounce off. Or they can run into each other, and then they'll bounce off of each other. They do not slow down like regular-sized things because they're not traveling through air. They're not rolling on a surface that has friction. They are the air. They're traveling through nothing, right? The only things they can run into are the other gas particles. And you can think of them as like being hard marbles. When they bump into each other, they're just going to bounce off. And so it seems impossible, but this just keeps going and going. It doesn't stop. Everything we see in everyday life, unless you put energy into it, it eventually slows down, right? You get a swing going really high, and you stop pushing it, and it just gets slower and slower and eventually stops. Gas particles don't do that because they have no resistance to work against. There's nothing to slow them down. So the size of a gas particle is negligibly small. It does have a volume, but the volume is so small that it really doesn't matter. So there is a lot of empty space between the gas particles. So an example is at STP, argon atoms would occupy 0.01% of the volume of the gas, and the other 99.99% would be empty, nothing. So if you scale things up and make an argon atom the size of a golf ball, the closest atom would be 4 feet away. And in between, there's nothing. So a golf ball, 4 feet away from another golf ball. Well, if this golf ball was the size of a tennis ball, and this was a tennis ball, would the difference in size matter when there's 4 feet between them? No. Or what if they were little tiny marbles or grains of sand? Would that matter? No. It doesn't matter at all. So the size of the particle doesn't matter. The average kinetic energy of the particles is directly proportional to the temperature in Kelvin. And that's one of the, never mind. So if you increase the temperature of a gas, you increase the average speed of the particles. So this is an average. Some particles are slow, some are fast. But the average of the particles is directly related to the temperature. Another important idea here is that a collision of one particle with another or with the sides of a container is completely elastic. And what that means is when they collide, they don't lose any energy. They can exchange energy, but they don't lose any energy. So if you think about a billiard table, a pool table, with the hard balls, right? And there's one sitting out in the middle, and you hit the cue ball, and it hits that ball. The cue ball's rolling over. It hits the other ball. And usually what happens is the cue ball kind of stops, and the other ball keeps going. There's a little bit of loss of energy because that's a big thing, and there's actual friction and stuff. At this size, there is no friction, and so the transfer of energy is complete. You could have the first particle that was moving come to a standstill and transfer all of its energy to the other particle. or it may transfer part of its energy and they'll just change directions. But you can have all these collisions and the average kinetic energy stays the same. Yeah, as usual, I got ahead of myself. There's the pool table. So these pool balls, billiard balls, collide and they bounce away. This is in contrast to, say, rolling lumps of clay, right? You roll some lumps of clay, they would need to be a little rounder than that. I think they're doing that just to help you understand that that's not like a billiard ball. This is soft stuff. You roll those at each other, and when they hit, they're going to go home, right? And they're just going to absorb the energy of each other and stop moving. You've lost all your kinetic energy. This is not what happens with gas molecules. This is part of the design of modern cars. There's a crush zone, right? So you hit something and the front part of your car just collapses like an accordion to slow you down so that you don't get collapsed like an accordion, right? But things stop. They don't like bounce off with the same amount of energy that they had before. The energy that's lost in this collision gets dissipated as heat. It's not that the energy disappears, but the kinetic energy is changed into heat. Any questions? So if we can embrace the ideas of kinetic molecular theory, then we can understand a lot of these properties of gases. So gas pressure. The gas particles are constantly moving. They strike the sides of the container. They have a force because they have a mass and they're moving. So they hit with a force. It's a very, very small force, but it is nonetheless a force. And so pressure is equal to the force divided by the area over which the force is applied. So you have all these little tiny particles hitting the sides of the container. The force is small, but the area they're hitting is also small. And so many are hitting the sides that it adds up to a measurable pressure. Boyle's law shows that the volume of a gas is inversely proportional to the pressure. So if we decrease the volume of the gas, that forces the molecules into a smaller space. They're still moving at the same temperature. They're going to hit the container more, meaning the pressure will go up. Volume gets smaller, pressure goes up. Just thinking about what the gas particles are doing. Charles' law, volume is proportional to the absolute temperature. Well, the temperature of the gas is proportional to the average kinetic energy. If we increase the temperature of the gas, we're increasing the kinetic energy. Kinetic energy is 1/2 the mass times the velocity squared. Increasing the temperature does not change the mass of the particles. It changes the volume, velocity, right? So you increase the temperature, the gas particles are moving faster. Now they're going to collide more frequently with the sides of the container, and because they're traveling faster, there's more force, right? So if you have your container set up to maintain a constant pressure, then the volume has to expand as you increase the temperature to keep the same amount of pressure. Avogadro's law, volume of a gas directly proportional to the number of molecules. So if we increase the number of gas molecules in the container, that's going to cause more collisions, right? This is talking about constant pressure. We're just looking at volume and number of molecules changing. In order for the pressure to remain constant, we have to increase the volume because there's more particles hitting the walls. Any questions? Dalton's law, also explained by kinetic molecular theory. Dalton's law is that the total pressure of a gas mixture is the sum of the pressures from each individual gas. So the particles of a gas have negligible size. They do not interact with each other. They just bounce off of each other. So particles of different masses are going to have the same average kinetic energy at a given temperature. The temperature is related to the kinetic energy. But if the mass of these particles is different, then their velocities will not be the same. So, same average kinetic energy, big heavy particles will be moving at a slower velocity. Tiny little particles will be moving faster. If you think about football players, right? You got the guy on the O-line that's like 300 plus pounds, right? He's awesome. But he doesn't run very fast. He's got all that mass to move. So the big guy runs slower, and then you think of the little running back, he's only like 180 pounds or something, and he's just running all over the place, right? So the small guy runs fast, the big guy runs slow. That's what the molecules do here. So the average kinetic energy is the same here, regardless of what the particles are. And if the average kinetic energy is the same, then the pressure is the same. So kinetic molecular theory implies the ideal gas law. And if you're interested in the derivation, it's in the textbook, but I'm not going to take time in lecture to go over that. What's really great about this is the theory predicts behavior that's consistent with observations and with measurements of gases. Scientific theory is the most powerful kind of knowledge. Now, is this absolute truth? No, it's not. But we haven't found anything that contradicts it yet. Right? That's how all scientific theories and laws are. They're constantly being tested, but we hold them as correct until they are disproven. Now, the model does break down under certain conditions. So it does not work at all temperatures and pressures, but it works at most of them in the middle. And by looking at where it doesn't quite work, we can get even more understanding about the gases. So again, kinetic energy is 1/2 mass times velocity squared. So if they have different masses, the only way for them to have the same kinetic energy is to have different average velocities. This URMS, this is the root mean square velocity. It's a fancy kind of average. So lighter particles travel faster on average than heavier ones. Yes?
Do we have to learn the relationship between volume and temperature? Or is it tied somewhere in the walls?
So the relationship between volume and temperature, you can create an equation for that by taking PV equals nRT and dividing by PV equals nRT. Cross out the pressures, cross out the N's and the R's, and there you've got your volume temperature law. So URMS is the root mean square velocity, just a fancy kind of an average. It's close to the regular average. You don't need to get into that. So this velocity, this average velocity of gas particles is proportional to the square root of the temperature in kelvins, and it's inversely proportional to the molar mass. So the square root of 3 times the ideal gas constant times the temperature in kelvins divided by the molar mass. And here, in order to make the units work out, the molar mass has to be in kilograms per mole, because kilogram is the base unit for mass in the SI system. Newtons have kilograms in them, joules have newtons in them, and then all the units work out. We've got this square root business here because 1/2 mv squared. We're essentially finding the v here, the velocity. So we're looking at the square root. So this graph is showing the distribution of velocity for different gases. So these would all be at the same temperature, and here's from not moving at all to going very, very fast. And so if we look at hydrogen, hydrogen's distribution is very broad. The root mean square, the average, is going to be out here somewhere. And so this is the smallest of those elements, and its average is going to be the highest. And then we've got helium and water and nitrogen and oxygen. So here with oxygen, we've got a much lower speed. The thing we want to notice about here is that as the velocity increases, as the molar mass increases, the variation in velocities gets bigger. So for hydrogen gas, we have a bigger variation, wider range of velocities than for oxygen. Any questions? Yes?
For the one before this one, it's the URMS. Why are the R not the 0.08206?
Oh, that's a great question. I overlooked that. Good catch. So here we're using R not as what we've been doing with 0.08206 liter atmospheres per mole Kelvin. This is joules per mole Kelvin. So a joule is a Newton, that's not an N. Newton meter squared? Let's see. Velocity is meters per second. Pardon me? Newton square meter. Newton meter squared. So then we've got this kilograms per mole. So what's going to happen here in the units is on the top we've got joules per mole Kelvin, and we're multiplying, we don't need that, times Kelvin. And then in the denominator we've got kilograms per mole. So the kelvins cancel each other, and the moles cancel each other, and we end up with a joule per kilogram. Well, Newton meter. Yeah, because the Newton has another one in it, doesn't it? I don't expect you to know these because I can't remember them. The Newton is a kilogram meter. Joule is Newton meters per second, I believe. I should make myself a cheat sheet for this. Newton meter?